It's okay, please.
Please. Hello, dear colleagues and friends. Let me announce the start of our session. So I have to check and make sure that all speakers are here and ready to present their reports. First of all, I ask our German colleagues, are you here or not? I mean David Waidner and Marcus Strand. First reporter.
Yes, I'm here.
Okay, okay. I would like to say you that first of all, I would like to introduce myself. My name is Eugene Briskin, and I am professor of Volgograd State Technical University, Russia. I would like to hear you. Please begin your report.
Okay. Just a moment.
What's happening?
Got to share the slides. Okay, can you see the slides?
I see.
Okay, so thank you very much for the introduction, Eugene Briskin. My name is Marcus Strand from Cooperative State University in Germany, basically in Karlsruhe, and I would like to present our paper with the title "Learning and Transfer of Movement Gaits Using Reinforcement Learning." The work was conducted by basically by David Waidner, a student of mine, and myself. Just a few words to our system, so maybe it's quite good to understand the background of it. Cooperative State University system is a universe based on the state university system in the US. So we have one base college in the local capital and several local universities and local campuses, and we are based in Karlsruhe, which is very close to the French border. And within this context, the students do very much practical work and study on the same time. So we have also quite strong relations to the local industry to do a theoretical and practical education. And within the campus in Karlsruhe, we have the Robot and Human Motion Lab, which is led by myself, where we consider basically robot motion and human motion in its context and interactions, like cooperative working and control of robots and something like that. And the work I present based on the idea how to train and learn a four-legged robot to walk without any dynamic model or anything, without explicit programming, just using reinforcement learning. And since this is a very hard and time-consuming work in the real world, the idea is to transfer the learning process into a simulation, but not specifically in the best simulation ever, just in a common simulation with some drawbacks, and see how the learning process performs and how we can transfer this to the real robot. So the robot is simulated in a virtual environment, and it learns with reinforcement learning specific movement gaits and tries to figure out the best method how to perform, and the performance is measured by the walking distance. So for us, the specific reward for the learning process is the walking distance with every step. After that, the learned behavior is applied to the real robot mirroring the movement of the simulation and figuring out which gaits work and how the process itself performed. So the real robot basically can be programmed without any manual engineering, without model building, without anything, just by simulation the environment. This was the basic idea, and we want to figure out in this experimental study how this idea works. As the simulation set up, we used Unity 3D engine with different plugins. For example, the physics environment for the physical simulation, like friction and stuff like that. We have very simplified collision models in order to get the simulation speed up, because it makes also not much sense if your simulation runs for like 1 year. We have to have simulations running for 1 day or less to have a specific performance, to be flexible and dynamic with our learning processes. Servo motors itself are not represented in the Unity 3D engine, so we use hinge joints with applied motor forces for this. And weights of the bodies, of the rigid bodies in the simulations, are based on the measured real weights of the real robot. And for the learning process, we use ML Agents Toolkit with its specific implementations of several reinforcement learning techniques. So basically, this is the robot. On the right hand, we see the detailed simulated robot with different joints and different parts. So we see each leg has 3 joints, one at the body, one shortly after, and parallel to that, one at the leg. And we have 4 legs. And for the simulation, we use the much more less detailed model you see on the left side, with much less triangles, and in order to have a performance in the simulation. So as I said, we use ML Agents Toolkit, and we figured out specifically 2 reinforcement learning techniques, which is soft actor critic and proximal policy algorithms. Reinforcement learning basically is the idea to do just something and see what happens. And if the result is good, we get a high reward. So if the robot moves with this performance, we get a high reward. And if the robot does not move or does something strange, we get less reward. So we want to maximize the rewards. And as I said, there are several algorithms you can use with several parameters. And these are the 2 we used for this simulation. What we also did is that we parallelized the training. So the implementation makes us capable to use 30 robots at the same time within simulation instance. And we had several simulation instances. So in result, we had 90 robots at the same time, with a total training time of about 6 hours with the less detailed robot model. And the interesting point is how the reward function will perform. So if it goes up, we have good reward, so we have good training. And if there is not a high reward, of course, this is not a good policy to use. So our reward signal, this is very important, is the forward distance traveled by the robot. After something about 40 million steps, which is a large number, but in simulation we can do this quite quick. As I said, in 6 hours, the training results maximized more or less, and the resulting movement gaits let the robot doing a movement forward with some specific strategy. It learned to do rather smart jumps, so from the back legs to the front legs. This is what he learned in simulation. And the best results, as I said, we achieved with these two strategies, with the strategies PPO, while the software actor critic strategy was not that good. In the end, the robot moved with 66 millimeters per second inside the simulation, and it, of course, is interesting how this will work in real time. To get some ideas about the different strategies, we see the figures here with the cumulative reward on the y-axis, and on the x-axis the number of steps, which is in millions. So we have 4 million, 6 million, 8 million, and so on. And we see different strategies with different parameters. And we see the two strategies, PPO in red and software actor critic in blue. And as you can see, what I said, software actor critic did not maximize the reward, cumulative reward anymore, while the PPO was still maximizing after something like 40 million steps, and is then going into some saturation. So how does it look like? I hope you can see the video. Probably not. Just let me check. Just a moment. Okay, maybe I can show the video later if you're interested in. I have some video about the learning process, which could be very interesting, but right now in Zoom, it's very hard to switch to the video within time. So we're going to transfer to the real world. So we have a robot looking like this with printed 3D parts with the specific joints. You can see the 3 joints on the base and 2 parallel joints on the legs. For 4 legs, it's a very small robot. And we control it with an ESP12F microcontroller for each Arduino platform. And the interesting point is the trained neural network is, of course, run on a connected PC, which sends the control commands to the robot. In the end, it turned out that the hardware setup was not modeled specific enough, or there was not enough power to do these steps. But if you hold the robot on your hand, you can see he's doing these movements, the learned movements, and with a higher power on the robot, the movements would also be fulfilled in a real world. So as the Unity 3D environment also communicates with the real robot in the same time, we can just replace the simulated robot with the real robot and use the shared code base. So it's very easy to learn and transfer to the real robot. And as we saw, the real robot performed the same actions as the simulated one, with some hardware limitations, which they have furtherly be discussed. And but we saw that basically the idea worked. So the robot mimicked these specific motions. We had these hardware setup problems, which we will get rid of in the near future. And we showed that it's basically possible to do this transfer from simulation in real world with simulated learning. Okay, so the conclusion, I think I already said, the time is over. So I want to thank you very much for your interest, and I'm happy to answer some questions. Thank you very much.
Thank you for your report, and I would like to ask anybody who want to ask a question. No, so I want to say some words. The problem of learning and self-learning of robots is in general, and the movement of mobile robots in a real environment, in particular, is one of the main problems in robotics. I and my scientific team are solving such problem also. Just like you, we are introducing a reward function, which we call the criterion of the optimal movement. We are introducing a discount factor, which we call weighting factors also. However, their values are quite arbitrary. We usually, with a smile, say, we take values from the ceiling. It's a joke. I would like to know how you choose discount factor.
You mean discount factor over time?
I don't hear you.
Or which discount factor do you mean in this specific?
No, I ask you how we choose discount factor.
As far as I understood it, it's based on the policy. So depending on the policy we use, we set this discount factor. In specific, I don't know. I would transfer this question to the student if you want.
Oh, thank you for your answer. And finally, I would like to know, do you know Carsten Benz? I met with him in Karlsruhe and in St. Petersburg. If you know, I ask you to send my warm greeting to him. Thank you.
To whom?
Carsten Benz.
Carsten Benz. Ah, okay. Yes, he's in Kaiserslautern right now, another city, but I know him very well. I can send best wishes from you. Yes.
Thank you very much for your report.
Okay. Thank you very much.